All right, welcome back. This is definitely the first time we're recording. So today we're going to be building traversal from in order and post order and in order and pre-order. And that's basically what your assignment 7 is, because in the assignment 7, you are getting 2 messages and you have to decode them, which will only build 1 message. So before I show you how to do this, let's talk about what makes us need to do this. So if we think back about last class, when we had a tree or something of the form of like H-E-L-L-O, hello. This is a complete tree, right? And because it's a complete tree, we can give the level order traversal, which is H-E-L-L-O, and it's unique. You can't build any other tree as long as it's a complete tree. But if it's not a complete tree, then you can build any other tree, because if it's not a complete tree, I could get the same level order traversal from that, which are different trees, right? This will also give you hello. I could also put the O like that. I could also make like a degenerate tree, like that. I can make many different trees. So the solution was to use the wildcard character. We use like a % in the assignment and said, make it a complete tree. And whenever there is something that should be there to make it a complete tree. So for example, if the tree we were looking to build was this tree. This is the tree we're trying to do right here. How do we represent it with a level order and still make it be unique? Well, to make it a complete tree, we need to have this here and this here full. So we just said just use that %. And then the level order traversal is hell %L %O. And this is unique, right? If the tree we were trying to build was this one, then we don't need this % here, right? Because it's still a complete tree without it. We do need this one though, over here. This one we need, but the other one we don't need, okay? So that's what we know so far. That's assignment 6 for you. Now here's the thing I don't like about this. First of all, I don't like having to need to use a wildcard character and having to force things to be a complete tree, because that's extra space, and also it's just annoying. And so what I'm going to show you today is how to build a tree from a traversal that doesn't require, I'm going to show you the algorithm, doesn't require using any wildcards. But there's a catch. Why did we use the wildcards in the first place? Because we needed to make it a complete tree so we don't have ambiguity. So the way we're going to work around that is, instead of building out of just 1 traversal, we're going to build it out of 2 traversals. And it's kind of like finding the intercept of those traversals that make a unique tree. And so the one that we're going to be focusing on, and these 2 algorithms are going to be basically the same thing minus 1 tiny change, and I'll show you. But ultimately, these 2 are the same algorithm, and it's building it out of both the in order and post order. And yeah, so first we're going to look at in order and pre-order. Yep, that's this one. Because last class I looked at post order first, and that way you have more examples. But we'll still do an example of each. So I before class started, I came up with this tree, and I did the traversals for it. And assuming that the traversals are correct, this should build a tree. So it's a tree of letters. There is one limitation to this algorithm, and that is that there cannot be duplicate keys, because otherwise it gets confused. I'm not sure about the workaround for that either, which is something that brings up in assignment 7. I was not thinking about that, but yet the messages work the way I give them to you. So as long as you follow the algorithm, then it should be okay. Okay. So we are missing letters. Oops. There's an I in there. I, J, R, L, Yeah, see, therein lies the problem. I have two J's in this one. Not to worry, I'll fix that. We'll make this J into, oh, that's a T. I got confused because it looks like that. Let's make it a K. So then this is a K and this is a K. All right. And then IJRLK. That KP. Okay, so we have 2, 4, 6, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Okay, so that looks about right. We'll see. So let me try to explain to you the algorithm before I just show you sort of like the systematic way of doing it. Let's analyze what each traversal gives us. So let's look at the pre-order traversal first. Well, first of all, remember the order of the things for pre-order. That is going to be your root, left, and right. And for the in-order is left, root, right, or left, print, right, however you remember it. So based on that, what can you tell me about the first letter or the first item or node in the pre-order traversal? It's the root. It's always going to be the root. So already you know that the root of this tree is going to be J, no matter what. You don't know the algorithm yet, but at least you can tell me that much. Okay. What about the in-order traversal? Now, this is not a binary search tree, but even though it's not a binary search tree, the in-order traversal says that anything to the left of the root has to be printed first, right? Everything to the left of the root has to be printed first. And then everything to the right of the root has to be printed after the root, right? Because it's left, root, right. So take care of all the left things, and then once you're done with that, print the root, and then take care of all the right things. So using that logic, could I guarantee that everything that is to the left of the root will be in the left side of the in-order traversal? So for example, let's say we have the following tree, ABC. What's the in-order traversal of this? BAC. A is the root. Notice that everything to the left of the root is also in the left side of the tree. And anything to the right of the root is on the right side of the tree. Is that always going to be the case? Yes, it'll always be the case. Because even if you had something like this, your in-order traversal of this is going to be B, C, D, E, F, and then A. And then if for something else here, an entire tree here, that would go after. You still have B, C, D, E, F, A, and then whatever that block of text is. So if you want to think about that this way, the in-order traversal is always going to have this order where A represents whatever the subtree is, and B represents whatever the subtree is. Agreed? Okay. Where is J in this in-order traversal? It's right here, right? Oh, that's not what I meant to do. Right? So then what can you tell me about these? They're all left of J, so they're going to be on the left subtree. So I can go ahead and rewrite this into the following tree. J, and then over here I have these. And over here, I have these. I don't know what order these go in, like individually. I just know this so far. However, if I was to tell you that E this E right here, if I was to tell you that that E was the root of these nodes here, then what could you say about G and F? That they're on the left side, and then O and I are on the right side. So if I have, back to our example of this. What?
It spells back.
What, like blood alcohol limit or something?
No, back.
So
Yeah.
back to our example of this. And then
Oh.
Back to example.
Yeah. Ta-ta. Drums. Okay. So ultimately, if I tell you that A is the root, you can draw this. What if I tell you that C is the root? You know that this is the case, but as you're saying, yes, we have multiple possibilities, because from that case, we could do something like this. We could also do something like this. We could also make A the root, or sorry, the child, and then have B over here, or B over here, right? Those are the four possibilities there. How do I know which one is the one that we have to do? Well, we need to know what the next sort of root of that subtree is. If I tell you A is going to be the root, then that eliminates two of the possibilities, and it leaves us with two of them, right? However, if I tell you that the A is the root because B is on the left side of the root, then this possibility gets eliminated and you're only left with this one. So that's essentially what the algorithm is going to do. How do we pick, though, between B and A, for example? Well, looking at this example, which is the three letters, the way we're going to pick which of these is the root is we're going to look at either the pre-order or the post-order traversal. With the pre-order traversal, we're working from left to right. From the post-order, we're working from right to left. Because remember, the post-order, the root is the last element, but it's the same thing. So it's kind of like a mirror version. So ultimately, if I tell you that the pre-order traversal of this is A, B, C, then we start out with A because that tells us that A is the root. And then we have to look at B. And we see that B is the next root, which in this case is quite a trivial example. But suppose that we made it a little bit harder by having a D there. So now, the in-order traversal of this is going to be D, B, A, C, and the pre-order traversal is going to be A, B, D, C. Right? So this is pre, and this is in. So I start out with the first element, left to right, and which tells me that this is the root. And because this tells me this is the root, I can generate the following, D, B, C. From there, the next thing that I'm going to pick is the next element. Because the fact that in the pre-order traversal, which says it's root left right, it tells me that before I go any further than the child of the first element, the root, I have to print it, right? So I print as I arrive at the nodes. I never reach, like, if I'm traversing a tree and I reach a node, I never skip it to print the children first. I always print the node before I visit the children, if there are any children. Because of that, I can guarantee that if B appears before any of the other letters, then this must be a direct child of A. It guarantees that, because you can't have like empty children. Like you can't have like a grandfather who just had a grandkid without like a child in the middle, right? You can't skip generations like that. So that guarantees that B has to be a child of A. Therefore, we knew that these two have to be there. This guy being alone guarantees that guy, did that wrong, my bad. I circled the wrong one there. We know that over here, I'll use a highlighter for that. These two are to the left, and this one's to the right. Because this one's to the right and it's alone, that's an easy giveaway that that's just a child. But because these two, we don't know which it is, because B appears first here, it guarantees that B is the direct child. So that's the one we're going to pick to be the child. So now it becomes B. And now where does D go? D could go here or D could go here. Well, within the in-order traversal of that, we know that D goes before B. Therefore, if B is the new root of that subtree, then D is on the left side and there's nothing on the right side. So you could say L and K here. The subset L would be anything that would be to the right side of B. This is right, yeah. And then K, anything to the left side. So because of that, it's going to be this one here. All right, so now we're gonna do the big example, but does everybody kind of get a feel for how it works? It's once you kind of see it, it's simple, but seeing it the first time is a little bit weird. So, okay, so we're gonna work our way from left to right in the pre-order. So we're gonna start with the J and work our way all the way to the P, and we're gonna use the in-order traversal to decide how to build a tree. But the algorithm goes from first element of pre all the way to the last element of pre, or in the post order, basically from last to first. But we'll do an example of that as well. Cool. So, as I had drawn before, I look at J because that's the root, and I sort of draw the first tree here, which is the G, F, E, O, I, and then R, K, L, P. The next item to look at is the I. Where is the I? The I is over here. That means that all of these people, or nodes, in fact, this is a different color for them, they are to the left of I, and then all of these nodes between the last root that we looked at and the node that we're looking at are to the right. However, that's an empty set, right? Because there's nothing there. But if there was, then that's what it would go there. What does that mean? That means that practically this tree becomes, I'm not going to draw this side for now. Actually, yeah, sure, why not? I'll draw it. Just a little more work. It means that I is the parent here, and then to the left side of that, we have the G, the F, the E, and the O, but there's nothing here. So this is empty right here. No child. In fact, I'll just put a little like X there to signify no, okay? Next thing I'm going to look at, that's not what I meant to do. Is G. Where is G at? G is over here. And this is recursive, as you can see. We're kind of recursively calling this. Okay, so G is the next root. So move that down. Which side am I going to put it on? I heard somebody say it, I think. The right side. Why? Yeah, because in order, right? Because right here is empty, and right here you got 3 spots. So, yes, very good. Okay, next thing I'm going to look at is the E. Where is the E at? The E is actually right in the middle there. Because that's the new root, that's quite simple. That just becomes E, F, O. Now, the way you're coding this, you probably don't know yet that these are of size 1. That's okay, because the next thing you're going to see is going to be the F. So you put the F, and then you see that there's nothing on this side, and there's nothing on this side. Then you put the O, and you see that there's nothing on this side, and there's nothing on this side. So recursively, you might not, if you don't have a check to see how big those sublists are, then you could have that extra call, but that's okay. Okay, so the next thing so we went ahead and we did the F and the O, technically. So the next one we're going to look at is going to be the R. The R's over here. Now the R is to the right. Now we're looking at the right group. We're looking here. Let me. Where's my? We can say of the master groups. This is one side, and then this is another side. Right. This is the big left, and that was the big R. So we're running out of colors here. But ultimately, we're looking at R. So between the root and R, there's nothing there, and then on his side, there's 3 of them. That means that R is going to be the parent of this set here. So that's convenient because we can just kind of bring that down. And which side is going to go on? As I said, there's nothing between J and R, so this side is technically empty. And then they're all going to go on this side, like such. All right, the next one is K. K is over here. Between R and K, there's nothing. And then there's 2 on this side. Like that. Then we got L. L is going to be the root between these 2. Where's P gonna go? Well, there's nothing here, and there's 1 here, so that means to the right of that. At this point, we reached the end of this traversal, and that means we have printed everything out. And there's our final tree. So we did the R is here, and then the K. Yep, okay.
Is that an X next to the K?
Yeah, they're all little null pointers per se. Just to signify there's no children, but you don't need them. I'm just kind of putting them. So that's actually, Yep. I actually had a different tree, but when I copied it, I flipped the K and L, which is okay because what we built was if it had been flipped. If it would have been L, K, P, then when we reach K here, then the L would have been on this side. But ultimately, it's still okay. This built a unique tree. So, yep. How do we feel about that? So, before I show you an example with a post order, which is basically just the same thing, the assignment 7, what is going to be is, you're still, at the end of the assignment, you're still printing the 7 traversals, which is pre-order, in-order, post-order, and level order. The reason, level order is the one you're getting. So really, you're only getting pre, post, and in order. Then you mirror the thing, and once you mirror it, you print again pre, in, and post, and level. So that's where the 7 comes from. And so, what I'm saying is, instead of getting the level order traversal to build a tree, you're going to have 2 of these traversals, and then you're going to build a tree out of that. So, I think one example, and because I guarantee you that it's valid input, as in it will build a unique tree, then I actually tell you which, I think the first example that I give you is a pre and in order, and then the second one's a post and in order. If I didn't tell you that, you can still build it, but you have to error check to make sure that it's, that, you know. How do you know if something is wrong, if it doesn't build a tree? Well, you start seeing, it's clear once you're actually trying to build it out of this, because like, suppose that you run out of here, but you're still with things here left, and you know, it gets messy. But ultimately, you would detect it because you finish a traversal and then things maybe printed twice or things like that. So you'll see it. In fact, you try it. Try putting invalid input in your code and see what happens. Just try it. You know, you might like it. So anyways.
So the objective of assignment 7 is pretty much building a tree either out of pre and in order or post and in order.
Yep.
So how do you verify if like the tree is built then? Is it like?
Well, how do you verify it? Like, as in when you're coding it,
Yeah, like how do you like know, like, oh,
do what I did. Do a tree by hand and then check and then test it on the computer and see if it actually builds the right way. Because when you print the traversals out, like for example, for the example that we did, I could print out the level order traversal, be like J-I-R. I could print all traversals from this and then see if the traversals that you get, because ultimately think about it. When you build a tree, if you printed all traversals, the combination of them should be unique. So not only should the pre-in order and in order match if you just build it using pre-order and in order, but if you manually by hand get the post order out and then compare it to what it got, that's how you guarantee that you didn't mess up.
okay.
So yeah, you'll have to do a little bit of handiwork. That's what I did at least when I was doing it, to make sure it worked. So in fact, if you want an example that you don't have to do by hand, you can take assignment 6 input, which gives you all the traversals, and then just get the pre-order and in order from that, and then feed it again. And then you should get the same output.
Oh, so like even though we're making a new tree, the output should still be the same as it was previously?
Well, you're not in that case, right? Because I mean, you're building the same tree that you built before, except now you're not building it from the level order. Now you're building it from the.
So we're just using a new method to build the same tree.
Yeah, potentially. Although in the assignment I give you different inputs so that it's cool because you don't get to see the same. More secret messages. Yeah. Yeah. Plus, I like the one that I gave for assignment 7. You'll like it when you see it. So, okay. Don't spoil it. Don't spoil assignment 6. Okay. So, let's do the post order one so we can move on to the test. Okay, so let me write these out. I'm going to read it out loud as I go so I don't make mistakes. 21, 92, 15, 45, 55. I had a 55? Yeah, okay. 77. That's a 66. 11. 22. And the in order. 42, 15, 92, 45, 22, 55. I found out why the bot was giving that "it will be done, my lord" thing with random messages. It's because I had like an order 66 thing, and so it was detecting 66 in URL.
Oh.
That's why I was doing that. I was like, why is it sending this message randomly? It just seemed like there was no pattern. Yeah, we still can't fully figure out why sometimes it doesn't respond to us. Okay, so this should build a unique tree that I have here. We'll find out. So the only trick with the post order that you got to switch the algorithm is you don't start from left to right, you go from right to left, because you know that the root is going to be the last element, right? That's the root. And now we're going to work our way this way. But that's it. Other than that, it should be copy and paste from the other function you make. Be safe when you copy and paste the recursive stuff, though. So, left of 22, right of 22. Okay, so now we can start. Well, we kind of already started, but what is going to be the next root that we're going to look at?
45.
What? Where you get 45 from? 11.
I didn't say 45.
I swear I heard 45. I'm hearing
I'll
things.
find it. No, actually, like 999 or something.
Well, there is a 45, isn't there? Yeah, there is a 45. So I was like,
10,000 trips.
so 11. So that means that is going to be the next route. So that's this guy. So that means that we have our less than group, or left, not less than, left side, and we got our right side group. So let's go ahead and redraw the tree. Okay. All right, now we are going to look at the next route, and that happens to be order 66 here. So that's that, which is this too. So technically here, our left side is nothing, and the right side is 77. Let's just copy and paste this so I don't have to keep doing this. Okay, that's it. We're done with that side, actually. Now we can work on the other side. Technically, we'll look at the 77, but no children on the 77, and no children on the 70 on the 55. So you're just gonna check them. You see that the 77 has nothing here, nothing here. You look at 55, it has nothing here, and that's pretty much that. Okay, everybody see where I was pointing to, right? Okay, so the next interesting one is going to be 45. Got 45. Left of 45, right of 45. Bam, done. Okay, the next one to look at, what color was the purple? 15. Where my 15 at? 15 that is right here. So left of 15, right of 15. In fact, here we can just highlight them. That. Okay, the next one we're going to look at is 92. 92, as you can see, has nothing on the left or right, so that's just that. Then we're going to look at 21. 21 is right here. That's an interesting one. It's right in the middle of them. That's convenient. What is that going to do? It's just gonna make the 23 be on the left side and the 42 be on the right side of the 21, which will pretty much complete the tree for us here.
Is a 42 meant to be a 41?
Possibly. Yeah. When did I get confused? Oh, I see. Yeah. Well, just make. I guess at this point, let's just make it a 42, because I think this is the only spot where I left it as a 41. Yeah, so let's just go with that to make it easy. I like to change every single thing. see if we make the same tree minus that 42 thing. So 22, 45, 11, 15, 55, 66, 21, 92, 77, 23, and 42 instead of 41. Yep, we did it. So as you can see, the only difference being that we went from right to left instead of left to right if it's post order. That's the. How would this break if we tried to make it? If we tried to use the post order for in order, or like if we try to use the post as a pre-order? Well, this would have made 23 to be the root, and everything will be to the right side of that. 42. So you probably build a tree. You probably end up with a tree if you did it this way. Where you get really nasty things is if you try to think of the in order as a post order or something, and then it's just like oof. So, but you built something out of it. So just be not the right tree. Any additional questions on this? Any additional questions on the assignment?
So in the assignment, we're given this in an array, right?
Yes, a character array, I
So
think.
we'll just look at the last one for this one, for the root, and then find it, and then.
For the post order and in order, you would look at the size of the array minus one. Yeah, that would point you to the last one.
And then scan the in order one for the root, and then take the left, put it to the left.
Yep, and recursively call that on
So-
sub list.
When we have like more than one item, would we not make a node? Would we do it only when there's one item?
Yes,
Okay.
yes. So it'll be recursive function, and you're gonna have to pass both lists. However, for the in order list, you don't need to pass the entire list. You can if you want, but really what matters is passing in the right indices, beginning of the list to the end of the list, and only when that is one is it actually an insertion.
Okay.
So, yep. It'll be interesting. It's not. It's an easy algorithm to understand, but it's a little bit of trickiness to implement. But that's the only thing you're really doing for a 7. So, like I said, 6 and 7 are kind of like the same one, but I split them. So, other questions?
Which assignment's supposed to be the hard one?
8's the hard one.
That's when you're balancing like.
Yes, that's what we'll talk about next lecture. But for now, this is where we're going to call it a day on this lecture so we can talk about the test. So, see you next time on the coronavirus series.